Okay, so now that I've given the exam back, let's go through logistics for today. So I'll say that today is probably the one day where I'm not going to say we're going to be here for the, I mean, we've been ending our Tuesday classes maybe a little bit early, and I'm not sure that's going to happen today because we're going to be doing some data processing today from a tensile test. And so let me talk a little bit about lab today, and then this will kind of make sense as to why we might be in here a little bit long. Okay, first off, let's just go through housekeeping. So we're not going to have class on Thursday. What I'm going to do on Thursday is I'm going to re-record that lecture where I went through the PCC lab report. So I haven't posted the PCC lab report on Blackboard yet because I wanted to have that video sort of recorded so that it was there so I could go through like what I'm expecting on the lab report and whatnot. So I wanted to record that. I'm also going to talk about aluminum on that recording on Thursday. Aluminum is the other alloy material that I'm going to talk about, but my aluminum discussion is really, really short. There's not a lot to say about it, so that'll be a really, really short discussion. I'll be honest, I might not post that video, or I might not get a chance to record that video until the weekend, but for our discussion, we're not going to have any class on Thursday, and everybody will be counted present, so you don't have to worry about that. We also do not have lab next week, okay? And the reason we don't have lab next week is because today we're doing 14-day testing. So we've done 7-day testing, done 14, and then we do 28. Well, next week is 21-day testing. We don't do 21-day testing, so we don't have anything to do. So we're not gonna have lab next week. So there you go. But I do want to go ahead. I do want to go ahead and do our lab today, where we're going to do 2 experiments. So we're going to do our 14-day testing today of our cylinders. So I'm thinking that'll go pretty smoothly because we've already done 7-day testing, so we're just going to do the same thing again. I've got data sheets. We're just going to do the same thing, record the data, post it to Blackboard, same as we've done before. But I have another experiment that we're going to do today regarding tension testing. So we're going to do a tension test in class today. We're actually going to do 4 of them, okay? If you recall, like this was in, like the very first week of the semester, we said, okay, let's look at a stress strain curve. So let's take a piece of steel, let's yank on it, and let's look at the yielding, the plastic deformation, the fracture, et cetera. And I told you we were going to do that later in the semester. Well, we're doing it today, okay? Now we're doing it today, but I'm going to be honest, from your perspective, the tension test is kind of like movie time because all we're going to do is show you the specimens we're going to test, we're going to put it in the machine, and we're going to test it. So from your perspective, there's not a whole lot you are going to have to do. We're going to be there, we're going to watch it, we're going to do it. But your requirements, what you're going to have to do is process the data later, okay? So you're going to take the data from the tensile test and then process it and do stuff with it. So what I'm going to talk about today is how to do that, how to take test data and process it and analyze it. The test data that we're going to analyze today is pretty simple. It's pretty straightforward. So it's a much smaller spreadsheet than you'll get from the Tenius-Olson. The Tenius-Olson is the tensile machine that we use in the lab. But our Tenius-Olson, what it'll do is it'll record the load deflection data and it'll spit it out to Excel for you. So it makes it pretty easy to process. But you do kind of need to know what you're doing there. Okay, so that's what we're going to do today. So in terms of lab, all we're going to do is our 14-day testing, and we're going to watch these tensile tests. We're going to do 4 materials. The 4 materials are steel, aluminum, brass, and then nylon. It's a plastic type material. So, okay, did everybody get the code? All right, one thing I'll mention before we pull this up, so if you have your laptop, I would go ahead and maybe like get ready for this, but I'll pull up Blackboard real quick. Let me see. Go to courses, materials. So one of the things you'll find, so I did want to show you 2 things. So if you go down here to lecture notes. So if you go to lecture notes, there's a topic here on structural steel and aluminum. And if you open that topic, what you're going to see is this data for this in-class example. If you've got your laptop with you, I would go ahead and download that because we're going to process that somewhat together today. It's not going to be incredibly challenging, and honestly, like what we're doing here is really, I mean, the data is not really that voluminous. You can honestly just recreate it yourself, but I thought it'd be kind of easy and a little smoother just to have that data together. And then the other thing I wanted to mention is how I'm going to set up the lab testing or the concrete report. So if you go into laboratories and you go down here to the PCC lab testing report, that's going to be the last folder. If you open this, you're going to see PCC test data, okay? And if you open it, what it's going to look like is this. Let me make it look like what you see. So a lot of the labs for me are invisible because I'm not in any of your lab groups. But if you go here, what you'll see is, so I've got fresh mixed data sheets. So these are your data sheets from last week. And then what I'll do is, so you all turned in the 7-day sheets today. What I'll do is I'll populate the 7-day sheets, then the 14 days, and the 28 days, so they're all right here. So that way everybody has the data and it's all readily accessible. Okay? Sound good? All right, just wanted to make sure everybody saw where that was. So, all right, and everybody got the code? Okay. All right, so let's talk a little bit about tensile testing and what we do with the data when we get it. Okay. So the tensile test is among the most ubiquitous tests that we perform on a material. Period. What we do is we take a predefined tensile specimen and we essentially yank on it at a controlled rate and record its response until we yank the thing in half. The actual specimen that we test can be a number of different configurations. It could be a plate, it could be cut out from a sheet. These are what are called dog bone specimens, so they're basically cut out of a given plate stock or whatnot. It can be round wire. There are even grips where you can yank on rebar and what have you. The specimen shapes or their cross sections tend to be either round or rectangular. The ones that we're going to test today have a round cross section, okay? And that makes sense because we'll use that fact here in a bit. But in terms of the dimensions and the specifications that we conform to, they're pretty controlled. We're going to be using the following circular cross sections, and so there's a series of designations for them. And so what we're going to be using, which is probably the most common type of test specimen that we use for a lab like this, is what's called an A505 tensile specimen. So when I say A505, so this is the configuration of the bar. So this is looking at the bar on the side. This term right here, A, is the diameter of the bar, okay? And we're going to be using an A505 tensile specimen. The 505 refers to the fact that the diameter is 0.505 inches. So just a little bit bigger than half an inch in diameter, okay? As for the length, okay, so we're going to use the length of the bar, and what we're essentially taking the length of the bar is as 2 inches. Now, I'm sure, so the length of the bar is this G dimension right here, okay? And I'm sure some of you are looking at this and thinking, that looks a little bit longer than 2 inches, Dr. Mike. Well, it does, but you have to keep in mind, so this part of the bar is completely constrained by the testing machine because we're going to screw those threads into the top and bottom. So it's totally going to be constrained and it's not going to stretch there. And what we're essentially doing when we define the length of the bar is we're essentially defining the length of the bar as this region right here that's sort of away from this bended region. We call that essentially our gauge length. So we're going to take the initial length of the bar to be 2 inches, okay? And why that matters is we need to be able to calculate strain. You all remember how to calculate strain? It's the change in length over what? The original length. And the original length is going to be 2 inches, okay? So with that, I want to ultimately sort of identify what we're going to try and do today. So our two main tasks are going to be to break down the data and generate a stress-strain curve, which is going to look something like this, okay? And then we're ultimately going to try and identify key facets of this curve, namely the Young's modulus, the yield stress, and the tensile stress. And what we're going to do for the yield stress is we're going to use an offset method. So I'm going to show you the offset method. We're going to use a 0.2% offset, but we're going to, you can use really any offset you want, and I'll show you that here in a bit. Okay, so with that, let's go through our example. I've given you load deflection data for a typical tensile test, and what I want to find is the Young's modulus, the yield stress, and the tensile stress. Okay, and the tensile stress is just the maximum stress on the specimen. So let me pull up the spreadsheet that I sent you. Okay, and it should look something like this. Is everybody able to access this? That brought their laptop? Okay. All right, so I want to go through what I've sent you. All I've sent you is load data and deflection data, okay? So, and to be clear, this is typically what is read out of a tensile test. And now, let's be clear, there are, I mean, you can set the, a lot of the testing machines to sort of just convert it to stress and strain. Some do, some don't, and I'd like you to sort of know how to do that. So I'm sort of giving you the most simplistic version of the data, and I want you to get something out of it. Okay, so that would be point one. Point two is that this spreadsheet only has, what, like 18 rows of data? Like, it's not that much. This is, yeah, I mean, it's, what, like 17 data points, 16 data points, okay? When I give you the spreadsheet from the Tenius-Olson for the 4 specimens that we test today, it's going to be hundreds of rows. It's going to be a lot bigger, okay? I'll probably talk next week about some things in that data set that you just kind of need to be aware of. So, for example, I'm giving you the forces in kips. It'll probably give you the forces in pounds and what have you. The other thing worth mentioning is that you'll need to know how to identify what's your zero. I'll talk about that when I give you the data next week. So, does that sound good? All right. Now I'm going to try and do this calculation in Excel, and I'm going to try and restrict all of my computations in Excel to sort of what's observably on the screen. So I'm not going to try and scroll up and down and do too much there. So the first thing I'm going to do is I'm going to insert about 4 rows up here, because I'm going to do some calculations up here because I want to have some base properties that I'm going to use across the board. Okay? So the first thing I'm going to do is I'm going to write down the initial diameter. So we'll call it D sub I. Okay? Now, we're testing an A505 tensile specimen, so remind me, what is the initial diameter in inches? Make sure everybody's been paying attention to me. 0.505. 0.505. Okay? So 0.505 inches. Okay? So now what I can do is I can say, all right, what's my area? Which is, we'll call it inches squared. That's going to be, how do I do that? Pi divided by 4 times that squared. Okay? So about 0.2. I'm sure everybody's, at this point, I'm hoping you all are comfortable enough with Excel that you all can handle that, all right? Okay. Last thing I'm going to do is I'm going to write down my initial length, which is 2 inches. Okay. All right. Everybody with me so far? Okay, so what I'm going to do is I'm lazy here. So this is just a little trick that you can do. I'm going to highlight column C, like I'm actually highlighting column C. How many of you all have ever used the paintbrush? The little paintbrush icon? So see where it says this format painter, it kind of looks like this paintbrush under the copy button. So if you highlight the format painter, and I'm going to format these 2 columns, now this is already, you know, formatted. Okay, first thing I'm going to do is, actually I said stress. Let's calculate strain first, then stress. And the stress is going to be in KSI. Now help me out. How do I calculate the strain. Tell me what to do. So essentially what I'm giving you is the deflection. So in other words, as the specimen is loaded, it starts at 0, and this is the change in length. So how do I convert this into strain? What do I do? I mean, what is the formula for strain?
Delta over L.
Delta over L. So if strain is delta over L, how do I fill in this column? What do I do?
You take the cell to the left of it, divide it by the 2 inches.
There you go. So we're going to take this, divided by that, and then what do I need to do that second cell? What's that?
F4.
Dollar signs. We need to F4 that. Or function F4 if you have a keyboard like mine. And then, boom. So there's my strain values. And what are the units for strain? There are no units for strain. Strain is unitless. Okay? Or you could say inches per inch or what have you, but that's unitless. So how do I get stress? What do I do here? There we go. So the load divided by the area, and then lock that in as well. All right. Good. I'm a popular guy. Leave me alone. Okay. All right. So we've got stress and strain. We need to plot this. Does anybody remember? Yes.
Can you do the strain equation again? It's kind of hard to see.
It's just the deflection over 2, change in length over the original length.
Okay.
And then the stress is P over A. Now, when you plot a stress-strain curve, what goes on the x-axis, what goes on the y-axis?
Strain is x-axis.
Strain is x-axis. Okay. So here's what we're going to do. I'm going to put the stress-strain curve somewhere down here. So what I'll do is I'm going to go to Insert, and then for the chart, we're going to do a scatter chart, XY scatter. There's a reason for this, but I'm going to use the one with this one right here, the one with straight line segments, but that has the data points. Okay, so and there's a reason why I'm doing that for this problem. So let's click this. Okay, and so we're going to select our data. Okay, we're going to add a data set. Okay, my X data is going to come from the strains. Y data is going to come from the stresses. Okay. And that's what it should look like. Okay. While we're at it, we're going to do a little bit more on the formatting side of things. So here's what I'm going to do. How do I want to do this? Let's do this. Maybe I'll add another row here. I'll just insert another row. You can do it however you want. But what I'm going to do is I'm going to take these cells right here, and I'm going to create a region up there, and I'm going to call this legend. And what I'm going to do for the first cell here, because I'm going to have 3 different curves that get plotted here, I'm going to call this test data. Okay? And the reason I'm going to use this is because I'm going to include a legend, and but that'll show up later. So if you want, what you can do is you can go to your chart design, and what you can do is for your data. So if you edit your data series where it says series name, okay, you know how, like, I think usually you probably leave that blank. What I'm going to do for series name is I'm going to set the series name equal to where it says test data, okay? And my reason for that is that if I go through and include a legend over here on the side, it says test data. Does everybody see that? I'm going to put my legend on the bottom, though, but you can put it wherever you want. There's a reason why I'm putting it on the bottom, though. And that'll become clear here in a second. Okay. Before we go down adding more stuff to this curve, there's a couple things I want to do to this curve right here. The first thing I want to do is I want to add some axes, or axes labels. So we'll go to axis titles. I'm going to call this strain. I'm going to call this stress. Put a unit on it. Okay. And the other thing I'll do is I'm going to add a title to the curve, and I'm going to say the title of the curve is stress strain data, and we'll say that this is A36 steel. And then maybe the last thing that I will do is the curve looks a little like squunched up right here. So what I'm going to do is I'm going to make it a little bit bigger. So we'll maybe do that. Maybe do that. That's probably good. And this part's maybe not totally necessary, but I'm going to click each one of these axes, make the shape outline black just to say that the bounds of the X and Y axes are a little bit more pronounced. Not really necessary for you, but we can do that. Okay. I'm going to give everybody a second on this because I know I just did a bunch of stuff here. So I'm going to give everybody a sec to just sort of make sure that you're caught up on this. So take a minute. Take your time. Check and see how everybody's doing in the wonderful world of Excel. That looks good. Okay. Looks like everybody, for the most part, is sort of knocking it out, okay? I'm going to maybe switch this in just a bit. Maybe move it over just a bit, because I know I'm going to use this space over here. Okay. All right. Like I said, I'm going to try and keep everything condensed onto this little region I've got here. I'll do my best to try and keep it all together. I don't want to zoom in and out too much. That's what I'm trying to do. So if you see me manipulating my graph a little bit, that's what I'm trying to do. I'm just trying to keep everything here. Okay. Now, this is my stress strain curve. What I need to do is identify some key values for the purpose of design. Okay? So let's identify those values. I'm going to sort of put, maybe I'll do something like this. Maybe I'll copy this over here, and I'll say values. Okay. Okay. So we're ultimately trying to define three quantities for this from this graph. Okay. We're trying to get the Young's modulus, Fy, and Fu. So let's start off with the easiest. The easiest is Fu. Remind me, what is the ultimate tensile stress? What is it? Like, what is that value? Like, how do you define? Like, if I give you a stress strain curve, what is Fy? Oh, sorry, Fu. What is it from this curve? What's it?
The largest.
The largest. So, how do we do that in Excel land? The max of what?
Stress.
Yeah, just the max of all this. That one's easy, right? Okay. There we go. That's one down. That one's easy. Okay. Let's talk about E. What is E? E is the Young's modulus. But what is the Young's modulus? What is it? How do you define what the Young's modulus is when you look at that picture?
Slope of that first portion there.
It's the slope of this first portion, as Mr. Allen said, 100% correct. So how do we do that in Excel? How do we do that? Well, let me ask you a question. How many data points comprise this first region? How many? 1, 2, 3, 4. Isn't that what we said? We said that the first four, or hold on. Actually, let me take a step back. Do you remember how, let me take a step back. So do you remember how when I said we're going to generate this chart, I said that instead of this linear chart, we were going to use this one? I wanted to be able to see the picture here, and I wanted to be able to see which data points. Okay? So I've got this one, this one, this one, and this one. So let's try something. How would I calculate the slope using this data here? How would I do that? How do we calculate Young's modulus? What's the formula for Young's modulus? What's that fundamental expression? Say it again, Mr. Parsons?
Stress over strain.
Stress over strain. So let's do stress over strain. And let's do it for these yellow points. Why am I doing those ones? Because those are the ones in the linear region. Do those values kind of make sense? What is the Young's modulus for steel? What did I say? Is what, about 29,000 KSI? Looks pretty good, doesn't it? Looks pretty reasonable. So there's a couple of ways that we can do this. Okay. So how do we go about this? Well, I say there's two approaches. We're trying to strike a line up like this. Okay, we're trying to strike a line up like that. So I say there's two ways. One, we could just pick one of these, or we could use linear regression. Y'all remember linear regression? Remember you have a bunch of data points, you try and fit a straight line? Y'all remember that from statistics? Did you know that there's a simple way in Excel that you can do that? Watch this. Equals slope. Okay? And what I'm going to do, so it's asking for known y's and known x's. I'm going to do the y's and the x's. And I'm going to include this yellow, or this one right here, because that's essentially, that yellow region, that's my line. Okay, that's my line. So if I get these 4 points, does everybody know what I'm talking about when I say linear regression? So linear regression is, I give you an XY coordinate system, I give you a bunch of points, and then linear regression is trying to fit a line that best fits that data. You all know what I'm talking about? So a simple way of doing that is to just use the slope command, because that's what it's doing. It's doing linear regression, and it's giving you the slope. Okay? So I propose that that's probably the best fit that we're going to get. But it also requires a visual inspection of the graph to know how many points are you going to account for, because you want it to be linear. Okay? Now, how do we test whether or not this is a good fit? Well, one way of testing it is to graph it. So, let's do that. Okay? So what I'm going to do, I'm going to set up myself a little table right here. I'm going to set a little table up right here, and let's see what happens. Unfortunately, I'm going to zoom out just a bit. That's good. Let's do that. Okay. Okay, so let me show you what I'm going to do here. All right, so my first point is going to be 0, 0. So ultimately what I'm going to do is I'm going to take this chart, I'm going to add a curve to it. Okay, so I'm going to put 0, 0. Okay, here's what I'm going to try and do. What I'm trying to do is I'm trying to add a straight line like this. Okay, so what I'm trying to do is I'm trying to test to see if this value that I got, if it hugs the linear region the way that it should. Okay, so how do I do that? Well, 0, 0. Okay, I need to draw this line up. It kind of needs to stop somewhere, so I'm going to pick a value. Let's pick 45. Right here. Okay, and the reason I'm picking 45 is that how would I calculate the elastic strain associated with that 45? Well, the way that I would do that is I would take 45 divided by the Young's modulus. Okay? So I'm assuming if this material were linearly elastic, if it was just a straight line, and I knew it went up to 45, how do I figure out the x-coordinate? Just take 45 and divide it by the slope. Okay? So what I'm going to do now is I'm going to add another curve to this. Okay? And I'm going to call this curve linear elastic. So under the legend, I'm creating a new box, and I'm going to call it linear elastic. So let's take this and let's add a new curve. So I'm going to click this, and I'm going to say chart design, let's select data, and let's add more data. So I'm going to add some data. When it asks for the series name, I'm going to call it linear elastic. The x values are just going to be those two. The y values are just going to be those two. And now look what I got. I got a nice little curve that hugs that linear region much like I want it to. Okay? And here's what I'm getting at. If I did this incorrectly, like here's my Young's modulus. Let's say I messed up and my Young's modulus was this. Or actually, no, let's make it really bad. Let's make it 2900. See, this doesn't look right, does it? That doesn't look right. The linear region needs to be tangent along with this. Does that look right? That looks right, doesn't it? So you can have some confidence that the Young's modulus that we computed of 29,381, that's a good data point. Okay? Everybody, that makes sense? Everybody with me on that? Okay. Now, how do we determine Fy? Okay, let's go back to the slides. So, a simple way to determine Fy is to use an offset approach. So what we'll do is we'll take that linear region, we'll offset it 0.02, or whatever offset that we want, we'll offset it that amount and see where it intersects. So how do we do that in Excel? How do we do that? Okay. Well, let me show you how we do that. So what I'm going to do is I'm going to take this table here of stress and strain, and I'm going to copy it. Okay, so a new stress strain table. Okay. Now let's talk about y-axis and x-axis. So for the y-axis, I want it to go from 0 to 45. So I'm going to use the same values for the y-axis as I do here. So how do I offset this a certain amount? Let's say the strain is 0.002. How do I take this line and shove it to the right 0.002? How do I do that in Excel? Maybe just take these values and add 0.002. So maybe what I'll do is have myself a little offset table right here. And then I'll say just equals that plus that. So that way if I change the offset, I'll just get a different answer. Now notice how it's formatting that as a percent. You can change that if you want. I can go here and just say, don't give it to me as a percent. Just go up here, give it to me as a number. Did that work? Well, let's see. Format or chart design, select data, add, oh, we need a name. So let's call this offset. Okay. So chart design, select data, add. Series name is going to be offset, X values, strain, Y values, stress. Boom. I now have an offset curve. And one of the nice ways of setting it up this way is if I change my offset, well, it's pretty easy. So for example, I'm using a 0.2% offset. What if I used a 1% offset or a 3% offset? See what it's doing? It's just shifting the line over, okay? But our standard offset is a 0.2%. Okay. Make sense? So I need to figure out what that intersection curve is right there. Now there are a couple ways of doing that. One way of doing it is to actually, get the x and y coordinates of this point, the x and y coordinates of this point, and treat this like an algebra problem. Figure out the point at which those two lines intersect. It's a 2x2 equation system. It's really easy. Or if we just need a simple value, this is what I'm going to suggest. Okay? Now, so that I don't mess around with this chart format, I'm going to copy it here. Okay, so I'm violating my rule a little bit, so I just copied and pasted the chart all over again. I want to show you something. So what has happened right here is, and along the x-axis, is Excel is trying to be smart. What it's doing is it's saying, all right, this is your data, so let's plot it from here to here and from here to here. But that's nothing to say that you have to do that, okay? So what I'm going to do is I'm going to change my x and y coordinates. For example, instead of going from 0 to 0.16, what I'm going to do is go from 0 to 0.01. And you'll see why I'm doing that. So I'm going to right-click, Format Axis, 0, 0.01. See what happened? So I'm sort of zooming in on where this intersects, okay? Now, I'm not really interested so much in where it intersects like this way. I want to know this value. So what I can do is I can zoom in, let's do this. Let's zoom in, format this lower axis between 34 and 35, 36. Okay. So see what's happening? See how we're able to really sort of hone in on where this intersects? See how it's between like 35.6, 35.4? So maybe what I'll do is go to that. I'll say 35.6, 35.4. Okay. 35.55. So see what's happening? See how I'm able to really sort of zoom in on what that value is? And I'm getting something like 35.572 or something. We can really zoom in on this if we want. So 5.7, 5.8. What was it? 5.6. Let's see. 5.7. So we're looking at like 36 point, what is that, 569? Something like that? Is everybody seeing what I'm doing here? I'm just changing the scale of the axes to really zoom in on where that intersects. So we'll call it 36.569. And if you want, what we can do is make this 0.002, 004, so we can really sort of identify what's going on. We're really trying to zoom in on that. 0.03. So I'm going to call it 35.569. So it's the same data, I'm just really zooming in. I mean, really zooming in on where those lines intersect. Was everybody able to follow how I did that? Everybody able to follow that? The reason I wanted to go through this is because I'm going to give you 4 data sets it's going to have more data points, but the process is exactly the same. So you're going to, convert it to stress strain. You're going to plot it. You're going to identify your slopes, identify your maximum stresses, and what have you. Make sense? Everybody okay with that? Any questions on that? Okay. I do have a couple things I want to say, though, about just some of the tests that we can do on top of this. So, getting chilly again. So, all right. So, one thing I'll mention is that ultimately what we're doing with a tension test is determining the elastic modulus. The elastic modulus relates stress and strain along the axis, uniaxially, normal stresses. We can do the same test, only instead of applying an axial load, we apply a twisting load. And the value there is we can relate the shear stress to the shear strain and get the shear modulus. I think you remember me talking about that in structural analysis right before the exam, how there's an E value and then a G value. So for steel, the Young's modulus is about 29,000 KSI. The shear modulus is about 11,200, something like that. We can mechanically relate the Young's modulus to the shear modulus with this term Poisson's ratio. You all remember Poisson's ratio? It's the ratio between, if you take a piece of steel and you yank on it, it'll get longer in one direction but thinner perpendicularly. And that ratio for steel is about 30%, so, or 0.3. Okay. I'll mention a couple of other tests that we do for metals. One that you will see mentioned a lot in Bridgeland. I'm curious, any DOH folks or anything, if you've heard the term Charpy test. Has that term ever popped up before? So if you ever get into design land, you'll hear the term Charpy mentioned a lot. But a Charpy test, so it'd be nice if we had one of the hammers to be able to do the Charpy test here. We don't. But a Charpy test is about absorbing energy. So the idea is that you'll fabricate a specimen of steel. It basically it's this rectangular little block of steel, and it's got this little notch cut in right there. And basically what you do is you have this pendulum hammer that, rises to a prescribed angle. You let it go, and then it fractures through the specimen. And what you measure is the amount of energy that it takes to absorb, the amount of energy that it takes to fracture the specimen. It's a very important parameter in fracture mechanics. It's also important related to fatigue, which happens a lot in Bridgeland. So it'd be nice if we had a hammer, but I also don't really know where we put it to. So I'll mention, so these start to get a little less common, at least on a material testing standpoint. You could take a piece of metal and bend it, undergo a flexural test. We'll do that for our big beam specimens for concrete, but we won't really do that for steel. And I'll be honest, from a material testing standpoint, I haven't really seen this done a whole lot, because a lot of times you can just get your standard Charpy test, your tension test and whatnot, and get all the data that you need. So I'll say that I will mention Rockwell hardness. I'll say Rockwell hardness. We're starting to get more into mechanical land. Rockwell hardness testing is for determining the hardness. It's more of a surface characteristic, so it's about preventing the surface from getting like dents and scratches, and so it's a material test to test the surface characteristics of a given metal. more important in mechanical land, but I mention it in case, you know, you might hear it in a civil engineering context. I had a couple of slides here related to corrosion and whatnot. I'll be honest, there's not really a whole lot to say behind corrosion other than steel rusts, and you need to prevent corrosion. I will mention there's a nifty little trick. A buddy of mine in grad school, he did some research on this called electrochloride chemical extraction. So the idea is that chlorides or salts penetrate the deck in West Virginia, and you can get corrosion and whatnot in rebar. And so essentially, I mean, it sounds kind of low tech. I mean, it kind of is, but the benefit was really cool. So if if steel corrodes, it expands, and that can cause significant degradation in a concrete element. Well, what they would essentially do is, I mean, it sounds kind of low tech, but they would, if they had any exposed ends of steel on either end of a given bridge, they would essentially hook it up to a car battery, and they'd have the cathode-anode reaction, and they would draw out the corrosion from inside the bridge to prevent that rust from permeating. I always thought that was really cool. But it worked, but it's also like you have to have exposed ends. There has to be certain conditions, and ultimately what you're doing, though, is you're just buying time, because once you start getting that level of corrosion, it's just a matter of time before you're going to have to replace the bridge anyways. So it bought you some time, but that was about it. I always thought it was really cool when my buddy Matt was doing that. So, okay. Any questions before we go down to the lab? Okay. Give me a few minutes to pack up. We're going to go down to the lab. So we're going to do your 14-day testing. So with regards to safety, just the same thing as last week, just eye protection, you know, all that. I've got your data sheets up here, but we'll do that, and then we'll have movie time for the tensile test. All right, give me a few minutes to pack up.